Hello friends, in our last video on electrodynamics we have discussed the electromagnetic induction and Faraday law, and in this video we will discuss the Maxwell equations, displacement current, theory of the electromagnetic waves and the transverse nature of electromagnetic waves. So we will discuss first the Maxwell equations. We already know that when the charges are in motion they are associated with the electric field and magnetic fields, and these electric and magnetic fields are interrelated or correlated, and this phenomena is called the electromagnetism. And to explain the properties of electromagnetic waves, the equations needed were put together by Maxwell, and these are named as Maxwell equations. So Maxwell equations are four fundamental field equations which are representation of basic law of electromagnetism. The first two equations are divergence equations and last two are curl equations. We can see here that first two equations, del dot E and del dot B, these are the divergence equation, and del dot E equal to rho by epsilon naught, that is Gauss law of electrostatics. Del dot B equal to 0, that is also known as sometimes Gauss law of magnetostatics. The third equation and fourth equations are equation of curl, del cross E and del cross B. So del cross E equal to minus delta B by delta T, that is the Faraday law, and del cross B equal to mu naught J plus mu naught epsilon naught delta E by delta T. So this is the extra term in Ampere's law. So that's why it is known as Ampere's law with Maxwell correction. The first three equations, 1, 2, 3, these were already studied in detail in our last lectures on electrostatics, magnetostatics and electromagnetic induction. And Maxwell found some problem with equation 4, and then he modified the equation with concept of displacement current. So we will see that how this problem was solved by Maxwell with this last law, which is known as the Ampere's law, but this modification term was added by the Maxwell. These equations are written for fields in vacuum, and in the presence of some material medium, then epsilon naught is replaced by epsilon and mu naught is replaced by mu, and then we can have some relation B equal to mu into H, D, that is displacement vector, is epsilon into E, and J, that is the current density, equal to sigma into E. So mu is the permeability, epsilon is permittivity, and sigma conductivity of the medium. And the concept of displacement current was introduced by Maxwell purely on theoretical ground at that time. And there was some inconsistency in equation 4 or in Ampere's law. We will see that how Maxwell found the inconsistency in that equation 4 or in Ampere's law. So in vector calculus we know that there is a rule that divergence of curl is always 0, and Maxwell tries this to equation number 3 and 4, which were the curl of E and curl of B, and the third equation was curl of E, del cross E equal to minus delta B by delta T. And if we take the divergence of this equation, so del dot del cross E will be del dot minus delta B by delta T, or if we take delta with in this differentiation, minus delta by delta T del dot B, or divergence dot curl E equal to minus delta by delta B of del dot B, but del dot B is 0 because it is equation number 2, the divergence of magnetic field is 0, and also curl of E, divergence of curl E equal to 0, and so left hand side and right hand side are 0, so equation third is correct. But when we Maxwell took the divergence of equation number 4, del cross B equal to mu naught J, then taking divergence means del dot del cross B left hand side equal to del dot mu naught J, that is mu naught del dot J. So left hand side is 0 because del cross B it is 0, but right hand side is not 0 because del dot J is not 0 for the varying current, and so this equation is correct for the steady current only, but for changing currents the equation is incorrect. So that's why he found some inconsistency in this equation number 4, or this is the Ampere's law. The inconsistency of Ampere's law was explained in case of the charging of a capacitor. If we have the capacitor plates and there is vacuum or air in between these two plates, but the current flows when there is some charging of the capacitor, and according to Ampere's law, this B dot dl line integral along the closed loop should be equal to mu naught into I enclosed. So according to this law, there should be no magnetic field between these two plates. And also we can see in this image also we have two plates, capacitor it is a capacitor, and there is a circuit which battery is there and it is charging the capacitor. So if we take the loop of this shape, suppose Amperean loop is here, and if we take the same surface like balloon, and we have two surfaces, S1 is making loop here and S2 is making loop here in between the plates. Then if we see for the S1, Ampere's law works for this this loop, but here for S2 it does not work, because in this case I is not there. There is no current between these two plates. I enclosed is 0, and according to this B should be 0 inside the capacitor region, but it is not true because there is some magnetic field between the capacitor plates. And also in last slide we have seen the divergence of Ampere's law, and mathematically we have seen that it was not true, and the divergence of curl should be 0, but we have seen that left hand side is 0 but right hand side is not 0 in this case, because del dot mu naught j j gives del dot j, mu naught is constant, so it will give mu naught del dot j, and del dot j is not 0 but del dot j equal to delta rho by delta t, that is the equation of continuity. So right hand side is not 0, that's why there is some problem with Ampere's law, and Maxwell suggested that Ampere's law is incomplete and it needs some correction. So now Maxwell modified the Ampere's law and he added some extra term in J, and it is known as JD, or the displacement current. So J equal to J plus JD, and JD was epsilon naught delta E by delta T. So mathematically if we take this equation and with an extra term, del cross B equal to mu naught J plus something, suppose this is capital X, and now if we take the divergence of both the sides, then del dot del cross B equal to mu naught del dot J plus del dot X, and left hand side is 0 because the divergence of the curl is 0, and right hand side is mu naught del dot J plus del dot X equal to 0. And if we compare this equation with the equation of continuity, del dot J plus delta rho by delta T equal to 0, and we have del dot J plus delta dot X equal to 0. So if we compare, then we have del dot X equal to delta rho by delta T. So this is the term we are looking for, the X, and in place of rho if we write del dot E into epsilon naught, then we have finally X equal to epsilon naught delta E by delta T, and this term is known as the JD, or the displacement current. Now after the Maxwell modification, the Ampere's law becomes del cross B equal to mu naught J plus JD, or mu naught that is equal to mu naught J plus epsilon naught delta E by delta T. So del cross B equal to mu naught J plus mu naught epsilon naught delta E by delta T, and this term is the conduction current. Conduction current means the current due to the flow of electrons, or simply the conventional current, and this is due to the change of electric field with time, that is known as the displacement current. So we can say that the changing electric field, it induces a magnetic field. It is similar to the Faraday law, when the changing magnetic field induces the electric field, and this is the modified form of the Ampere's law, and this is also known as the Maxwell's fourth equation. Now we have to find out the magnitude of the displacement current, that is ID. So ID is the current between the capacitor plates, and I is the current in the circuit through the resistor and battery, and this E, the electric field between the plates of the capacitor, equal to E equal to sigma by epsilon naught, and it is sigma means Q by A, so Q by epsilon naught A. So and the displacement vector D equal to epsilon naught E, it is Q by epsilon naught A into epsilon naught, that it is Q by A, and the displacement current I equal to J into A, because JD is equal to delta D by delta T, and it is epsilon naught delta E by delta T. So if we put A and JD is equal, put in place of JD, we can write delta D by delta T, and A into delta by delta T of D, that is Q by A. We have just from equation 2, and it is delta Q by delta T, and delta Q by delta T is the just the conventional current I. So ID equal to, I means the current flowing in the circuit is equivalent to the current in the gap, or the current between the capacitor plates, that is the displacement current. So displacement current provides a continuous path for the charges across the capacitor. So that's why there is a continuous current when we are charging this capacitor. So Maxwell equations are summarized in this table. So most of the time the differential equations are important. Del dot equal to rho by epsilon naught, and the integral form is surface integral E dot dA equal to Q by epsilon naught. This is the Gauss law of electrostatics. In differential form, del dot B equal to 0, and in Gauss law for magnetostatics, that is surface integral B dot dA, total flux through a closed surface is 0. Faraday law, E dot dl equal to minus delta phi by delta T, and in differential form it is del cross E equal to minus delta B by delta T. And the Ampere's Maxwell's law, means the modified Ampere's law by Maxwell, is B dot dl equal to mu naught I plus mu naught epsilon naught delta phi by delta T, or in differential form del cross B equal to mu naught J plus mu naught epsilon naught delta E by delta T. So these are the 4 set of equations which are Maxwell equations, and these are already well known laws in physics. Now we will understand the physical significance of Maxwell equations. So Maxwell have correlated the electric field and magnetic fields, and he described how the electric field can create a magnetic field and vice versa. And the first equation is known as the Gauss law of electrostatics, and it tells that the net quantity of the electric flux leaving a sample volume is proportional to the charge inside the volume. So we have already discussed it in our electrostatics lectures, that it means the charge distribution generates a steady electric field. So due to a charge distribution, there we have a electric field, and phi equal to Q enclosed by epsilon naught. The flux through a closed surface is related with this. So flux phi equal to E dot dA. So phi equal to E dot dA equal to Q enclosed by epsilon naught, or in differential form we can write it del dot E equal to rho by epsilon naught. So this first equation is Gauss law of electrostatics. The second equation is the Gauss law of magnetism, del dot B equal to 0. So it tells that the total magnetic flux through a closed surface is 0, and it suggests that the magnetic monopole do not exist separately as it was in the case of the electric charges. As we have seen that the electric charges, we can have the positive charge and negative charge. They can be they can create some field separately, but in case of the magnet, we don't have the separate north and south poles. They are always together. And Gauss law indicates that there are no source or sink for magnetic field inside a closed surface. So del dot be equal to 0. Here we can see that if we have magnet, so they are making the closed loop. So if we make any surface at any place, then the lines once coming out from one side, and the same lines are coming inside from other side, so it will make the total uh, uh, flux is 0. Whereas in the case of uh, the charges plus q and minus q, they can work as a source and sink, because the lines are coming out from plus charge q and negative q, it is coming they are converging. So it was the case in the case of the electric field, but in the case of magnetic field, there is no divergence or no convergence of the lines, and the magnetic field is solenoidal because the divergence of B equal to 0, and field lines are closed lines, and they make a loop. The third equation is Faraday law of electromagnetic induction, and we know that voltage induced in a closed loop is proportional to the rate of change of the magnetic flux in the loop, and every time the magnetic field changes, there is a creation of electric field. So we have seen that in this, that if we have a solenoid and the magnet is moving here, then there is some kind of current is there. Electric field del cross E equal to minus delta B by delta T, and a changing magnetic field can induce an electric field like Faraday induction, and the negative sign here is due to the Lenz law. The fourth equation is Ampere-Maxwell circuital law, and Maxwell modified the Ampere's law and added an extra term in Ampere's law, that is the displacement current. And we can see in this equation that del cross B equal to mu naught J plus mu naught epsilon naught delta E by delta T. So this extra term is known as displacement current, and the magnetic field induced around a closed loop is proportional to the electric current plus the displacement current that the loop encloses, and this displacement current is due to the change in the electric field delta E by delta T. And this equation means the magnetic field is generated by time varying electric field, and we have seen that a current conducting wire, it creates some magnetic field here, but for this charging of the capacitor, we have no current inside this capacitor, but still it have the magnetic field created between these plates. So it is due to this displacement current. So electromagnetic waves, before the Maxwell theory, the electric field and magnetic field was assumed as the separate things, and Maxwell unified the theory of electricity and magnetism and proved that they are both correlated. And electromagnetism is all about the four equations which relates the electric and magnetic fields. These are known as Maxwell equations, and there may be multiple wave equations possible for these two fields, but only those fields which satisfy these four Maxwell equations, they are electromagnetic waves. Maxwell found that electromagnetic waves travels with the speed of light c in the vacuum, and we know that waves travel with some vibration, so electromagnetic waves also travel with some electric field vibration and magnetic field vibrations. And we can see that if the electric field vibration in z direction here and the magnetic field vibrations are in x direction, then there is the movement or the traveling direction or propagation is in y direction, and from here to here it is the one wavelength, or it is the length of the electromagnetic waves. In this slide we show the wave, the basic term used for waves, and a wave is a disturbance that moves energy from one place to another. So only energy is transferred, not the matter. It is the property of wave. And if we consider a simple sine wave, then we know the terms. What is wavelength? It is the distance between two crest or two through, and this is the amplitude, and this is all about the wave. And the waves travel along the medium, but electromagnetic waves, they can travel it in vacuum also. And there are two types of waves. One is transverse wave. They have oscillations that are perpendicular to direction of motion, and like the case of a rope, if we give some vibration to rope, then they are the transverse wave. And also electromagnetic waves are transverse. Seismic waves, they are earthquake waves, they can be transverse. And longitudinal waves have oscillations that are along the direction of the wave traveling. And it is the examples are sound wave and seismic waves. In that case, the vibrations are in same direction of propagation. So now we will discuss the electromagnetic wave, or the theory of electromagnetic wave. And for explanation of these waves, we need some kind of wave equation, because Maxwell equations are coupled equations in E and B, so they cannot be solved. So therefore they should be uncoupled, and we can get the equations either in E or either in B field. So we have the Maxwell equations in free space. Free space means when we don't have any charge or any current. So rho equal to 0, J equal to 0, mu equal to mu naught, and epsilon equal to epsilon naught. So for vacuum, del dot E equal to 0, first equation, del dot B equal to 0, del cross E equal to minus delta V by delta T, and del cross B equal to mu naught epsilon naught delta E by delta T, because J and rho, they are 0. So these are the equations for vacuum or free space. So if we take the curl of this equation, third equation, so del cross E equal to minus delta by delta T del cross B, and this left hand side will give us, this is like A cross B cross C. So by vector properties, it is del dot E minus del square E equal to minus mu naught epsilon naught delta 2 E by delta T square, because we have replaced del cross B equal to mu naught epsilon naught delta E by delta T using this fourth equation here, del cross B. And now we have, because del dot E is 0, if we replace here, then we have only these terms are remaining, minus del square E equal to minus mu naught epsilon naught delta 2 E by delta T square. So this is the equation, del square E minus mu naught epsilon naught delta 2 E by delta T square equal to 0. This is the wave equation for electric field, and this epsilon naught mu naught has the dimension of the velocity. So we can write delta 2 E minus 1 upon V square delta 2 E by delta T square equal to 0. So this is the wave equation in electric field. Similarly, we can find out the wave equation for the magnetic field also. And for the magnetic field, we have to take the curl of equation number 4, that was del cross B equal to mu naught epsilon naught delta E by delta T. So if we take the curl of both sides, so del cross B equal to del cross mu naught epsilon naught delta E by delta T, and again if you use the vector properties, del dot B minus del square B equal to mu naught epsilon naught delta by delta T of this del cross E, and del cross E equal to minus delta B by delta T, and del dot B equal to 0. And if we put these values in this equation, now we have minus del square B equal to minus mu naught epsilon naught delta 2 B by delta T square, or we can write delta square B equal to epsilon naught mu naught delta 2 B by delta T square, or if we take it left hand side, del square B minus 1 upon epsilon naught mu naught delta 2 B by delta T square equal to 0. So this equation is the wave equation for the B field or magnetic field. So equation number 7 is the wave equation for electric field, and this equation number 10 is wave equation for magnetic field. And we have seen that delta 2 E equal to mu naught epsilon naught delta 2 E by delta T square, and delta 2 B by B equal to mu naught epsilon naught delta 2 B by delta T square. So these are the wave equations in vacuum for E field and B field. And if we compare this equation with the general wave equation, the general wave equation is like del square psi equal to 1 upon B square delta 2 psi by delta T square. So it is valid for all kind of waves which is traveling with some velocity v and which have wave function psi. So if we compare this equation with these two equations, then we can see that 1 upon B square equal to mu naught epsilon naught, and B square equal to 1 upon mu naught epsilon naught, or B equal to 1 upon under root mu naught epsilon naught. And if we put the values of these coefficients, mu naught, that is the permeability of free space, that is 4 pi into 10 to the power minus 7, into epsilon naught, that is 8.85 into 10 to the power minus 12. And if we calculate it, it is B equal to 3 into 10 to the power 8 meter per second, that is the speed of light in vacuum. So this proves that light is an electromagnetic wave, and mu naught and epsilon naught are constants. These are already were used in Biot-Savart law and Coulomb's law. These coefficients were already known. So electromagnetic waves, they travel with the speed of light, and it was great achievement that time that Maxwell calculated it theoretically, and it was matching well with the experimental value. And the solution of these differential equations are sinusoidal plane waves. So we will understand what are the plane waves and what are the solution of these wave equations. Now we will briefly discuss the electromagnetic wave spectrum and monochromatic waves. And the electromagnetic wave spectrum has broad range of waves starting from radio waves to gamma rays depending on their wavelength and energy. And we can see that the visible region is only from 400 nanometer to 750 nanometer. The wavelength is in this range, and this is the light which can see from our eyes. And the violet color have lowest wavelength and red color have highest wavelength, and the energy and the wavelength are correlated with this equation E equal to h into nu or hc by lambda. So if we know the frequency or wavelength, then we can find out the energy of a wave, electromagnetic wave. And if we take the single frequency f or omega, omega means 2 pi f, then it is known as a monochromatic wave. And the white light or the sunlight which have combination of all the colors, it is known as the polychromatic light. The plane waves, they vary only in the direction of the propagation, and they are uniform in planes normal to the direction of propagation. Suppose a wave is propagating in z direction, then this is uniform in xy plane. So xy plane, this is constant, and only the variation is in z direction. And in electromagnetic waves, we can see the vibrations E and B, these are in this plane only, one plane, and not in the direction of the propagation. So electric field and magnetic field vibrations, they are confined in this plane, and whereas the variation or wave is propagating in third direction. And the equations E and B for the monochromatic waves can be defined E equal to E naught e raised to power I kz minus omega t if the wave is propagating in z direction, and B equal to B naught e raised to power I kz minus omega t. So E and B are expressed in terms of k and omega, and k means the propagation vector and omega means 2 pi f, that is the frequency. And in general, we can write for 3 dimension E RT equal to E naught, that is the amplitude of E, E naught I e raised to power I k dot r minus omega t, and B equal to B naught e raised to power I k dot r minus omega t, where E naught and B naught are amplitudes and they are also complex. Their amplitude are also complex, and the field should satisfy the wave equation for B, E and B. And k is the propagation wave vector and omega is the angular frequency. So omega by k is denoted by c, that is the phase velocity of the wave, and lambda equal to 2 pi by k. And the phase velocity omega by k of electromagnetic wave is equal to speed of light c in free space or vacuum. So this is the solution for the monochromatic plane wave in E and B. Now we have to prove the transverse nature of electromagnetic waves. So we already know the Maxwell equation for free space, del dot E equal to 0 and del dot B equal to 0, and del dot E means dot product of del with the electric field vector, and in last slide we have seen the electric field vector was E naught e raised to power I k dot r minus omega t. So it is the general solution in electric field. So we can solve it in Cartesian coordinates. So delta by delta x I plus delta by delta y j cap plus delta by delta z k cap, and this E is also complex amplitude, means it have the component EOX I plus EOYJ plus EOZ k, or E naught xi plus E naught yj plus E naught z k cap. So this amplitude is complex into e raised to power I, and k and r also, in 3 dimension k can be written as kxx plus kyy, kxi plus kyj plus kzk, and r can be written x, that is position vector, xi plus yj plus zk, and if we take the dot product between these two vectors, we get the e raised to power I kxx plus kyy plus kzz minus omega t. And now we have to take the dot product between these two vectors, and now delta by I dot I will give us the result delta by delta x e naught x e raised to power I, this whole term will be here, I kxx plus kyy plus kzz minus omega t. Similarly, delta by delta y of e naught y, and this whole term will be again there, e raised to power I kxx plus kyy plus kzz minus omega t, plus delta by delta z of e naught z and e raised to power I kx x plus kyy plus kzz minus omega t. So now we have this equation, so we have just to take the partial derivative and rearrange the terms. So if we take the differentiation of this term e naught x, first we have to take e raised to power x, have the differentiation e raised to power x, and then the differentiation of this term. So it will give us e raised to power I kx into e raised to power I kxx plus kyy plus kzz minus omega t. So this term will be all in these three terms. So finally we will have this kind of equation, e naught x e raised to power I kx plus e naught y I ky plus e naught z I kz, and this common term e raised to power I kxx plus kyy plus kzz minus omega t. And now we, for this term we can write kx into eox plus ky eoy plus kz eoz, we can write it k dot e naught or k dot eo. So this is the product of dot product of these two vectors, can be written like this, and here we can write this also, it was in component form, and we can write it k dot r also. So e raised to power I k dot r minus omega t, and if we compare this del dot e, so del dot e was 0, left hand side is 0, so right hand side is I k dot e, because we have replaced this e, means e naught e raised to power I kr minus omega t here. So k dot e is here. So left hand side is 0, it means right hand side should be also 0. So k dot e should be 0. So k vector means propagation vector dot e equal to 0. It means if the dot product of two vectors is 0, it means these two vectors are perpendicular to each other, means k vector is perpendicular to e. Similarly, we can prove that del dot B is 0. From this equation we can also find again B equal to B naught e raised to power I k r minus omega t, and using that equation again we can find the propagation vector k dot magnetic field vector B equal to 0, means k is perpendicular to magnetic field vector B also. So we, from these two equations we have proved that k dot E equal to 0 and k dot B equal to 0. So we can say that the electromagnetic field vector E and B both are perpendicular to the direction of propagation vector k, and it proves that the electromagnetic waves are transverse in nature. And also using this figure we have already seen that if this electric field vectors, they are perpendicular to direction of propagation. Suppose it is moving in this direction, so electric field vectors are perpendicular to direction of propagation. And also the magnetic field, this blue color line vibrations, these are also perpendicular, because with this propagation direction this z axis and y axis are also perpendicular. So this shows that the electromagnetic waves are transverse in nature. So we have proved it mathematically, k dot E equal to 0 and k dot B equal to 0, and from this diagram we can also understand the electromagnetic waves are transverse in nature. So in our previous video we have discussed the electromagnetic induction and Faraday law, and in next video we will discuss the energy in electromagnetic waves, the Ponting theorem and Ponting vector. So thanks for watching this video, and if you are new to this channel then please subscribe so that you can know about the new topics which are related to electrodynamics and engineering physics, and also on nanotechnology and some Bible questions for the experimental physics and B.Tech courses. Thank you very much.